Well, thanks, Guillaume, for this introduction. It's always a pleasure to be, to participate to PLMCM and to be in Clermont-Ferrand, even if it's only virtually. So today I will show you our results about photonic Landau level in strain honeycomb lattices. So this work has been done mostly in Lille, so where I am in the group of Alberto Almo. And it has been done in collaboration with Elena Rosas from Dortmund, the group of Jacqueline Bloch in Palaiso, and the theoretical support from Grazia Salerno in Brussels, Jacopo Caruso in Trento, and Tomoki Ozawa in Sendai. So I will start with a brief reminder on the quantum Hall effect. So quantum Hall effect has been discovered in 1980 by Klaus von Klitzing in a semiconductor heterojunction. He discovered that in a two-dimensional electron gas under constant magnetic field, the Hall conductance is quantized in units of the elementary charge and the Planck constant. So one way to understand this problem is to look at the energy spectrum. So here it's composed of flat levels equally spaced in energy. They are called Landau levels, and the Hall conductance is proportional to the number of field Landau levels. So several years later, in 2004, the field of quantum Hall effect experienced a revival with the discovery of graphene. So graphene is a two-dimensional honeycomb lattice of carbon atoms. And if we look at the energy spectrum of graphene, it's composed of two bonds touching each other at specific points of the Brillouin zone called Dirac points. And near these Dirac points, the dispersion is linear. So we are dealing with massless Dirac quasi-particles. So because of this linear dispersion, when we apply a magnetic field, we have something very different from before. Now there is a Landau level at zero energy here, and there are higher order Landau level below zero energy and above. So a few years later, Guinea, in this paper, proposed a way to study quantum Hall effect in graphene without magnetic field. He proposed to use strain like this one, which is a trigonal strain, to induce a strong gauge field acting as a uniform magnetic field. So with this technique, you can reach a very high value of magnetic field, like you can see in this paper. One particularity of this synthetic magnetic field is that it doesn't break time reversal symmetry. Since this strain, in fact, is only creating a gradient of hopping in the lattice, we can transfer this technique in graphene analogs based on uncharged particles like phonons. So there is a paper from Wen in 2019 where they study Landau level in acoustic graphene, but we can also transfer it to photons. So up to now, there is only one paper dealing with this, with strain engineering. So it's by Rechman in lattice of coupled waveguides. And in this paper, well, they use a trigonal strain, as you can see here on the lattice, and they excite on the edge and observe some localization due to Landau levels. But here, some very interesting features of photonic Landau level remain unexplored, such things as the Landau level spectra, the wave function, and propagating edge states. So how can we design this synthetic magnetic field? So one easy way is to use a linear strain along X. So as you can see here, we will keep the hopping, the transverse hopping T2 and T3 equal over all the lattice, and we will put an increase of the hopping T1 along X, a linear increase of this hopping, following this formula, okay, where tau is the gradient of the hopping evolution. So if you do the mathematics that you can find in this paper, you achieve, you will see that the synthetic magnetic field you get is directly proportional to this gradient tau. And this synthetic magnetic field has opposite sign in the two Dirac points K and K prime. If we look at the bond structure of a strain ribbon with zigzag edges here, we can find the bond structure of Landau level in graphene. So with this n equals 0 Landau level here at 0 energy, above we can see here high order Landau level, and below 0 energy we can also see Landau levels. So in between, in the gap between Landau levels, we can see some propagative states that are localized on the edge. So they are called helical edge states. So now I will speak a bit about our system. We are using two-dimensional semiconductor microcavity with gallium arsenide quantum wells. We etch this microcavity into pillars. Here you have the energy spectrum of one pillar, the luminescence, and you can see the different photonic orbital, the S, the P, and the D orbitals. So these pillars, in fact, act as photonic atoms. So we can couple two of these pillars, and we will get something like a diatomic molecule with the hybridization of this s orbital that gives rise to two modes, a bonding one and an anti-bonding one. So they are separated in energy by 2 times J, which is coupling strength. And this coupling strength, we can change it very easily by playing with the interpillar distances. So we can design lattices like this one. So to study these lattices, we use a non-resonant excitation. So polariton will fill the energy bands, decay, and we will look at the far-field emission. Here you have the emission of the S bands, okay, in this lattice. You can see here polariton Dirac cones here. And if we compare with the graphene energy bands, here you can see it's very similar. So we have here graphene analogs with polaritons. So what is great in our structure is that if we go higher in energy, we can see another set of bonds called p bonds coming from the coupling of p orbitals. And in this set of bonds, we also have polariton Dirac cones. So how can we design this strain and this synthetic magnetic field? Well, we during the design of the lattices, we the distance between pillars here is larger than the distance between pillars here, okay? So this gradient of interpillar distances will create a linear evolution of the hopping along X, T1, so following again this formula, and it will create a linear evolution in the S band and also in the P band. So it means that we will have a synthetic magnetic field in S and P bands for the same lattice. So we designed several lattices with different gradients. So here you have a microscope image of a non-strain lattice. So the synthetic magnetic field here is 0. And here you have the images of two strain lattices that we have studied. You can see that the higher the strain is, the narrower the lattices are. And this is because we are limited, the lattice width is limited by the merging of Dirac cones that happens when the hopping along X is twice larger than the transverse hopping. So if you want to know more about this merging of Dirac cones and the exotic transport property associated, you can watch the presentation of Bastian Rial Thursday. So now I will show you our experimental results. So I will compare the data from a non-strain lattice without magnetic field with the data of strain lattices with magnetic field. So starting with the dispersion, in the unstrained lattice, we can see, well, at 0 energy, we can see the polariton Dirac cones, okay? And if now we go to the strained lattice, we can see something very different. So if we focus at the position of the Dirac cones marked by the dashed lines, and if we look at zero energy, which is this region, we can see something that looks like n equals 0 Landau level. So we cannot see the high order Landau levels here because the line width emission is larger than the gap between Landau levels. So to confirm that this is really the n equals 0 Landau level, we can look at the wave function. So here, starting with the case with no magnetic field, the dispersion, well, we are pumping these 6 pillars, and you can see that the wave function is delocalized, okay, because of the very high group velocity of polaritons, and the intensity from the sublattice A here and sublattice B is the same. Now, if we go to the wave function recorded at zero energy with in the strain lattices, so with the synthetic magnetic field, you can see that it's very different. We have a clear asymmetry between the A and the B sublattices, and it's also very clear in this very high strain lattice. So this B sublattice polarization is the main signature of the n equals 0 Landau level under synthetic magnetic field. Okay, so we can see this n equals 0 Landau level, but we cannot see high order Landau level because of the line width, and of course we cannot see the propagative edge shades that lie in between. So we can go to the p-bands, because in the p-bands the hopping is larger, so we will have more energy space between Landau levels, so maybe we can see something. So again, starting with the dispersion, well, in the unstrained case, we can see the polariton Dirac cones. If now we look at the dispersion recorded in the strained lattice, we can see again something very different. If we focus at zero energy and close to the polariton Dirac cone, here we can see something that looks to n equals 0 Landau level. If we go slightly below, we have a gap, and below we have another flat band, almost flat, which is in fact the n equal -1 Landau level. So again, to check that we can see this Landau level, we can look at the wave function. So starting with the unstrained case, so without synthetic magnetic field, again, the wave function is delocalized, and it's very similar to the wave function of S-band, but here we have the p orbitals, okay? So now if we look at the wave function recorded in the strain lattices, we can see again this sublattice polarization, okay? So here you can see the px orbital, and this is in fact the b sublattice. So all the light, most of the light comes from the b sublattice. And it's also very clear in this very high strain lattice. So again, we have this B sublattice polarization, which is the main signature of n equals 0 Landau level with synthetic magnetic field. So now I want to speak a little bit about this propagating edge state, so that we can see here in between the Landau levels. So they are called helical edge state, and it's contrary to a real magnetic field where the time reversal symmetry is broken and where you have a chiral edge state. With synthetic magnetic field, we still have this time reversal symmetry, and thus we have helical edge state. So it's a pair of counter-propagating current on each edges. So to study them, we can excite the lattice on the edge. So here I will compare the dispersion. Starting with the excitation spot on the left edge, we can see a strong emission from this flat band, which is in fact the zigzag edge state degenerated with the n equals 0 Landau level. Then we have a gap, and below we have another flat state, which is n equal -1 Landau level. So no sign
Omar,
of... Yes?
You just have maybe 2 minutes left,
Yes.
more, I would say.
Okay, perfect. So here you can see that there is no sign of propagating edge state. On the contrary, if we put the excitation on the side, on the left, the right edge of the lattice, then we can see a clear and strong emission from this propagating edge state. So to confirm this, again, we can look at the wave function. So if we put the excitation spot on the left, we can see we can't see propagation. In fact, we can see only the excitation spot. If we go on the right edge, then you can see here that polaritons flow towards the top and the bottom of the lattice. So we have this n equals 0, it equals edge state only on the right. And to understand this, well, we have to think and we have to remember that our Hamiltonian is chiral. So chiral symmetry means that the wave function is localized only on one sublattice. And if it's the case, then the state will be at 0 energy. So if we want to have a propagating edge state, we need something that is not at 0 energy. So we have to mix the Landau level, which is on the B sublattice, with something that is on the A sublattice. And in our case, it's the zigzag right edge state, which is in fact composed of A sublattice. Okay, so now I will conclude. So we have observed Landau levels in honeycomb lattice of photonic resonator exposed to an artificial gauge field. We have seen the sublattice polarization of Landau level n equals 0 in S and P bands. And finally, we have observed helical edge state induced by the gauge field. Thank you.
Okay, thank you very much, Omar, for the talk. So now we have a few minutes for questions before the break. So if there are no, well, while you are thinking about your questions, I will ask myself maybe one. So on this right side, you have a propagation in one direction and in the other direction, but this direction of propagation should be related to some pseudo spin somehow. So is there a way to measure this spin component and to show that okay, really these spins are opposite somehow in one okay, on each side of your spot?
Well, it should be possible, yes. Yes. Yes.
Okay.
Looking at the, yeah, yes.
Maybe to some sublattice pseudospin, I don't know, measure some quantity related to this, and one has to discover which is a good quantity to measure. But okay, we have a question by Olivier Bleu that you know very well.
Hi, Omar. Thank you very much for your talk. Yes, so I have a small question. This is related with this sublattice polarization.
Yes.
Do I understand well that this is, let's say, B polarized because you are looking at a given value in graphene, let's say K prime or K, and that in the opposite value, this polarization should be opposite?
Well,
something else?
In fact, because of this synthetic magnetic field, the wave function has the same sublattice polarization in the two Dirac cones. So that's why here, in fact, we are not selecting a given Dirac cone, and we have contribution from the two, and we have still this B sublattice polarization. So it's the main difference with a real magnetic field, where the wave function here should be should have equal intensity on the two sublattices. So if you want to see the other sublattice polarization, then you have to change the sign of the gradient. So instead of going like this, if you put a gradient like this, then you will see a sublattice polarization.
Aha, so the symmetry is related with the gradient. Okay, thank you.
Okay, so well, there are no. Okay, last question by Sergei Alyatkin. Last question. So yes, you can.
Thank you very much for your talk. I have a question. What do you expect if you increase the lattice constant, and then you again organize stretch lattice, because you are working here in some specific regime where you have this Hawking amplitudes.
Well, if you mean if we increase the interpillar distance?
Yeah. Because at some point your cells, they will become isolated, and there is some intermediate regime. Do you expect something interesting in the band structure?
Here, if we want to keep the this tight binding nature of the Hamiltonian, we need to have an overlap between the micropillar. So if we increase this interpillar distance too much, then, as you said, we will have a localized, the link between pillar will be very weak, and I'm not sure we will see this type of energy bonds.
Yeah, but the question is still you will not be able to consider this system in a tight binding approximation, but there must be some transition between isolated pillars and this tight binding wave function. So the question is, do you expect that there might be something interesting in comparison the normal micropillars and stretched lattice of micropillars?
Well, I don't have a clue. I don't have a clue on this.
Thank you.
Okay, so thank you very much again. I think we need to stop now the session. So